So we understand I/O. We understand how I/O is connected to IPC, and now we want to look at a finer grained issue. Um, and not all IPC is how it's connected to remote assignment IPC. And now we want to look at a finer grained issue, which is, do we have blocking IPC or non-blocking IPC? And that's going to distinguish the socket usage that you've done in 431 or 524 was the course that I taught, and the implementation you will do in assignment 6, which will be non-blocking. So blocking is a concept we know now pretty well. Okay, blocking removes thread from ready queue and makes it state non-ready. Where the thread goes, that depends on the kind of blocking. And why do we have blocking? There's really two reasons, and we've seen them both. There might be sister intervention. If the thread is trying to access a critical region, especially if it's doing so in the operating system, we want to block it, right? So it may or may not, it didn't. The application didn't say it wants to block, but it needs to block just to make sure that things are safe. Okay, and our synchronized methods allow us to do that in Java. And sometimes we want blocking. We do blocking because the application wants to blocking. It doesn't want to proceed any further. Okay? The thread wants to be blocked, and that's why we have this wait and signal operations in Java. And in the case of IPC, or many other operations, and many other, especially well, any operation actually, we can talk of synchronous versus asynchronous operation, and if that has to do with the meaning of the operation, and if the application invokes a synchronous operation, it's saying I want to block. That's what I really want. Okay, and underneath there might be a wait call to implement that. Okay, so there's blocking, the term blocking, and there's the term synchrony. There's blocking operations, there's synchronous operations, and we see that blocking is sort of a lower level thing. It can be done for synchronous operations and system. It can be done because the system decided it should be done. So let's try to understand synchronous operations and how they might differ from blocking operations. So what is synchronous versus asynchronous? That's a term you'll see often and hear often in computer science, not just in the context of I/O or distributed operations, in terms of any operation. And it has to do with the fact that each operation has an operation defined start time and an end time. Okay, so at some point the operation starts, at another time it ends. And somehow these two times are involved in distinguishing between synchronous and asynchronous operations. Okay? So put on your thinking hats and try to figure out how you might use these two times to distinguish between synchronous and asynchronous operations. How might you define these two kinds of operations based on these two times? So we assume that each operation has a start and end time. Synchronous operation invoker waits until the operation finishes, just like John Rich said. Asynchronous, I'm not using his definition. I'm making it the opposite of synchronous. Operation invoker does not wait until completion. It could wait, but not until completion. And you might say, why would you ever do that? Okay, but at least theoretically, practically, this may or may not be interesting, but we'll see it is interesting practically. Asynchronous just means it's not synchronous. That means we did not wait till it finished. You either unblocked immediately, or you unblocked when some other event occurred that is of interest, but that was not the completion. Okay. And like John Ray mentioned, if there's a result, then some other operation needed to wait for result or completion. And even if there's no result, if you want to get completion status, okay, then you need something else. And John Ray mentioned that in JavaScript you can have callbacks invoked that go and tell you when the operation, the result of the operation, or if the operation doesn't have a result, the status of the operation. Okay? So asynchronous becomes more complicated, and often people that's why go for. So blocking. So an operation can be blocking, okay, which means that it may block the invoker, which means it makes the invoker wait, unblocking possibly before, until, or after operation completion. So you could block potentially after the operation completion, though I don't know of any system that does that. Um, but you could block before, and so you can have a blocking operation that is not synchronous. Okay, at least theoretically, just because I said any if the invoker unblocks before time t2 uh, and after time t1, then it is a blocking operation. Okay, so synchronous operations always imply blocking. I mean, when I say that, I mean that synchronous operations can always block. I mean, if you're doing a synchronous get C and the character's already been input, then you don't block. You know, you have the character because the completion occurs at the same time as the initiation. Okay, but if the two times are separate, then the synchronous operations are blocking operations. But blocking operations are not always synchronous operations. Okay, because you can block till some event occurs and that event is not completion, it is some earlier event. And it could potentially be, like I said, event afterwards. So, yes, that's interesting from a theoretical point of view, but we can see why somebody might want to wait until completion. Why would somebody want to wait for some event other than completion? And that becomes a question. So what are some logical? So it's certainly not, a particular time instant. It is some logical time, some logical event. So what can be these logical events that are of interest? And let's go and see those. So this has to do with, and we'll talk about IPC. Okay. So we're sending a message, we're sending and receiving messages, and what are the various phases in the lifetime of a message? So that means that we have to understand what the communication pipeline is like. Okay, something that has been hidden from us so far. So let's look at that. So I've started the discussion with remote assignment, and this blocking, non-blocking concept applies to both remote assignment, which we're going to study in depth, and RPC, which we've already seen before. Okay, so this is a more general concept. Okay? And remote assignment, like we see on the left, some expression gets assigned to a variable, whereas on the right we have some message triggering a method call. So when the operation starts, the expression is computed and put into some data structure of the application. And if that is a method request, then the message gets put again in some application data structure, and it just happens to have a different format. It's intended to be a request rather than an expression. Okay. From there, it is going to go to the network through the operating system, through the kernel, and it has to be in a buffer that's accessible to the kernel, and typically that is a separate buffer from the application buffer. So it has to go into the system buffer of the source operating system. Okay, so that's where it goes. Now it goes over the network, and if the message reaches the other end, it reaches a buffer in the operating system. Okay, and from there, at some point, it goes into data structure accessible to the thread. Okay, so that's the communication pipeline, which is going to give us the events that can cause unblocking. Okay. And this is at this point, the operation gets started at the remote end. Okay, um, the operation got started at the local end, at the sending end, much earlier. Okay, but this is where it starts at that end, and when the assignment completes, or when the method completes, that is when the operation finishes at both ends. Okay, so we see now a bunch of times that can be times at which we unblock. Okay, so the variable has been really assigned that value, and the method has been invoked. This is where when the operation finishes. Okay, and between these two times there are these events. So in RMI, we are at this end. So both the message sender and receiver block until the remote method completes. Okay. In Gypsy, which is what your A5 is about, this is what happens. The Gypsy semantics is the same as RMI semantics for function calls, as we've seen. But for procedure calls, they're more like what John Ray mentioned in JavaScript, that the message sender does not block, just issues operation and returns. Okay. So there must be a reason why Gypsy does it that way and RMI does it another way. There must be pros and cons. And we see, and I'm sure you guys are thinking of these pros and cons right now. And because of various pros and cons, you have all of these as valid points at which we might want to unblock. And let's try to just understand this remote procedure call and blocking, but that's something we've already used. So let's just, before we try to answer the question about the pros and cons of different times, let's try to understand how this, how a particular blocking semantics that we've used actually works. Okay. So let's assume the first case where there is the remote server is waiting for a message, okay, and the client decides to send the message, which is a request to invoke a method. Now it's going to wait till the operation completes. Okay, sorry. In this case, what's happening is that it sends a message, and the remote end has not yet started waiting for the message. Okay, so it waits till the remote end decides to receive the message. The remote end might be in the middle of executing some other call, and there might be only one thread, and so it's going to go and finish the previous call and then wait for the message for the next call. Okay, so this is a situation opposite of what I said earlier, that the receiver starts waiting after the sender waits. Okay, the receiver then executes the code. Okay, so at this point, both parties are waiting. Okay, when both parties are waiting at the same time while the receiving code is being executed, we say they are in rendezvous. Okay, so this is a technical term that was invented in the context of a language called Ada, which I mentioned earlier. And then when the receiving code finishes, they both unblock. Okay, this is the other end situation where the receiver started waiting for a message to arrive, and when the message arrives, it executes the code, and at this point, both are waiting, and they are in rendezvous, and so rendezvous occurs in both cases. In one case, the sender waits for a longer time. In the other case, the receiver waits for a longer time. Okay, so you see that there's waiting involved in both cases. Okay, so actually to make this symmetric, I should really have had the word wait here because I've got the word wait here. So so in both cases, the code is being executed here, and this is the part that's waiting. But this wait was a longer wait. This wait occurred before rendezvous in the client, in the caller, and this wait occurred before rendezvous in the receiver. But there is going to be a wait that both parties do while the code is being executed, and that's the rendezvous. Okay. So we understand a little bit about synchronous operations when they are method calls. So receiver may make the sender wait before rendezvous, and sender may make the receiver wait before rendezvous. And they both wait during rendezvous. Okay, so that's the Ada rendezvous. Okay, now let's try to answer the question. What are the pros and cons, if any? I mean, these are theoretical times. Maybe they're not practically interesting events. So why are all of these, or which of these are valid times to unblock? and why, and the answer is, well, for this kind of application, this is the kind of time that might be of interest, and for another kind of application, another kind of time might be the right time. So think about this. That's a complicated question. We have one, two, three, four, five times. So we need to discuss each of these times and say, well, is that a time that should cause unblocking? Okay, so put on your thinking hats. Okay, so sender knows operation is finished. Okay, that's a guarantee that they may need. So if you're making a reservation on an airline, or if you're trying to save something on Google Drive, I do that. I don't just go in. I wait till Google Drive has said that it's finished before I shut my computer off, just in case something bad happens, and some bad things have happened to me in Google Drive. So I'm careful. Um, so here the guarantee is that the receiving process, it reached the destination and the process is alive because it has consumed the thing. And as long as the operation doesn't kill the process, the operation will happen. Okay. So if I'm starting an animation which takes a long time, I might not want to wait till the animation finishes, but I want to just guarantee that the animation really started. And if then the animation doesn't start, maybe I'll get some other kind of feedback from the user. Buffers can get full, okay, and messages may not reach computers. So you might want to know for sure that the message reached the destination machine, the machine is alive. And so for Dropbox, I have much more faith in Dropbox than Google Drive, even though Google Drive gives me much more space, so I use it more. But once I know it's reached the server, I might just relax and say, okay, it won't do anything bad with my file. Okay. And system buffers can get full. This telepointer here, I can send a lot of events to you guys, and I might not care that each message reaches you because there's not that much there are events that are going to follow it that convey the information also. So so if I'm sending telepointers, I just want to make sure that there is um, data, there is system buffers, and I want to slow down my communication if I'm flooding the system, because that's just going to make the system go slower. Okay, so I might want the system to block me if I'm hogging the network. Okay, and hogging the buffers. And if I'm sending load averages, so let's say we have multiple grading servers for 533, and each grading server goes and says this is how much load average says how many threads I have or how many processes I have. Let's say these are different machines. So how much I'm being used right now. So I might want to go and send this information to other parties or to some central process, saying that this is how busy I am. And if one or two messages get lost, no big deal. I'm sending this information periodically. So I don't want to wait, and I just go and start the operation. I know I'm sending these averages periodically, not sending the telepointers. Um, that I'm not sending information that will flood the buffer, so I might not want to block it. Okay, so I've actually seen PhD theses that have uh, argued for each of these times, and there used to be a big debate at one time in 70s and mid 80s, I think mostly in 70s, about what is the right, and early 80s, what is the right time to block. Okay, and as I think mentioned a few times, after sockets came around, that whole research on IPC mechanism just kind of died, and that was the mid 80s. And we still see sockets today, even though, as we've seen, they are still confusing to people. And simpler abstractions have existed. And I mentioned the Go programming language, and it uses CSP abstraction. So uh, just because sockets are so popular doesn't mean that they are the right abstraction, and there are pros and cons. And so I kind of assumed one event that we need to argue about. Why do we have the data in both the sending buffer and the system buffer? It's clear why we need this at the source. Um, it's clear why we need these two buffers here, because the message may arrive before this buffer is being even created. But here you create this buffer and then you copy to this buffer. Why do this copying? Why not just use this buffer directly? We did see that the kernel has to be involved in sending messages on the net to the network, using the network driver. And we saw the kernel space and user space. We saw kernel mode and user mode. And we saw that in user mode, you can't access kernel space. But in kernel space, you can access user space. That, in fact, that's how your page tables get loaded, or your pages get loaded. Okay, the pages are in your address space, and the kernel copies the data to your address space. So, given that the kernel can access this, why do we need a system buffer? And we don't always need a system buffer. Okay, we sometimes need the system buffer. So the question really is, when do you need the system buffer, and why is it not always the center buffer? So think about this question, because buffering and synchrony are very related to each other, and so buffering and blocking are related to each other, as we've also seen. So try to think of this. So uh, if the sender does not block, it can override the contents of the buffer before original contents have been sent. That's what Jason said. And of course, if it is overwriting, it better overwrite it using critical sections, and we can't guarantee that there's a critical section. We can't guarantee the application is using critical section. So the overwrite may be unsafe. So Jason's argument was that the second image might be sent, and John Rui's argument is that it might be some mixture of the first and second image, because there was no critical section there. Okay, so by having a separate system buffer, we guarantee that the data are not overwritten, and so we don't even have problems about concurrent access. Okay, so we can put a discipline on the application and say, if you do this stuff, it's at your risk. Okay, so and when we look at NIO goes and basically allocates it asks the system to go and allocate a buffer for it directly, and it writes to that buffer, and it is not supposed to go and override that buffer till that buffer has been used. Okay, and there's data structure in the buffer to indicate how much of it has been written, how much of it has been read by the system. So and that's for efficiency reason. It does have the danger that the application may misbehave, but as long as the application doesn't misbehave, we can have our cake and eat it too. Okay, so that's actually a concept that NIO has, that the original Unix sockets didn't. Okay, so I get into this buffering, and what's the time? Is it 4:45? Yeah, it's 4:45, right? So let me just take 1 minute here to finish this thought. So an implication of this is that if the reason why we couldn't use the sending buffer was because the application may misbehave and overwrite it. But if the operation is waiting, then we know it can't do something to the buffer. So we need an allocate a system buffer, and so we don't need a system buffer, and we are guaranteed there's no flooding. So we might want synchronous operations not only because they're easier to code, but just because they're more efficient in this way. But then they become inefficient in another way, that we can't go and we have to wait for every unit of data that is sent to actually reach the system the other end. If you're making it a synchronous operation, and we can't coalesce the data into a single message. So if you're writing 10 bytes, we have to go and wait till each byte is received by the other end. We can't coalesce the 10 bytes into one message. So it becomes inefficient another way. Okay. So in byte communication, we don't wait till the data reaches the other end. We just wait because that would not allow coalescing. We wait for an event that's earlier than that. Okay, so this shows you the relationship between blocking and buffer. Okay, and when we have when we do allow coalescing, then there has to be an operation like flush that says, hey, don't wait, please do send the data. I want it to, because coalescing can only happen if messages don't get sent when the application requests them, but they get sent at some later point, and you can flush buffers to go in. Okay, so we'll continue from here next time. And by the way, last time I had some trouble reaching the other Zoom link, so I've got now a different computer for it. So please don't go away if I don't log in immediately. And if there's no one there for the first 5 minutes, I'll just close that link. Okay. So I'll talk to you guys now in office hours. Did anybody have any question for the rest of the class at this point? Okay. So on to office hours. So last time we looked at the difference between synchronous and asynchronous operations. And we also saw that all synchronous operations are potentially blocking, but some asynchronous operations may also be potentially blocking. So blocking does not imply synchrony. And if it doesn't imply synchrony, then they must be for the same operation multiple blocking times. And that's what we saw, that an operation can have a start time and an end time. And so you could block till when the operation starts, and when you're talking about IPC, when the message that you're sending and if you're doing a send, it's a system buffer at the source site, and then it's at the buffer at the destination site. Then it's in the process. It has been accepted by the receiving thread, and then the operation is completed. Okay, this is an operation involving two parties. So, so we get into buffering also. We're not only interested in blocking, but also buffering. And as it turns out, these two concepts are related. So the size of source and destination system buffers is an issue, and we'd like to keep the system buffers as small in number as possible. So if we have a synchronous operate, if we have a blocking operation, um, and if you have a synchronous operation, of course, but if we have a blocking operation, uh, then and the blocking operation involves uh, waiting until the uh, message reaches the destination site, then basically you can keep that. We don't have to go and copy the data from the sending buffer to the kernel buffer. We can just keep the data here till they have arrived at this point. Okay, sometimes you need to retransmit the data also multiple times. So you need to sort of keep the data around here until you have some acknowledgement that the data have reached. Okay? So that way we could eliminate kernel space for these buffers, and that would be more efficient, okay, in terms of space. So that's what we can get rid of. And we can't have a situation where a thread just floods the system with buffers. Okay. The flip side is, and this gets aggravated, particularly when we are sending bytes, is that we can't delay sending the data till we have enough data to send. So if you're sending byte by byte by byte, if the user thread is making requests per byte, you have to essentially send each byte, because you don't know when the next byte is going to arrive, and 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 uh, and sorry, you have to wait till the byte reaches, and so you are sending too many messages. Okay, so you can't coalesce, you can't wait and say, okay, well, let me just wait for this much time, and if within this much time I get more data, I'll send all these data together. So that's a disadvantage of having this approach. Okay, and that's why systems that provide byte communication do not provide synchronous operations of this kind. Um, okay, and when you do, when the system is delaying sending of messages, then there may be times at which the application would really like the data to be sent. So these operations typically provide a flush operation also that go in that forces the data to go across the network. And if we're writing to a local file, then a similar flush operation forces data to be written to the disk. Okay. So what we've seen here is basically gather scatter. Okay. The application sent a message. The channel, which is this abstract idea we are talking about, is motivated by sockets, but we are working at a higher level. Doesn't quite send the message at this point. It waits a little bit. And if there's another message, then it can send these two messages together in one packet, one unit of communication. And so sending system may gather if possible. And these data may arrive as they were sent from the sending site. And then if you really want to distinguish between the two units, if you, often in byte communication, you're accessing a stream of bytes, so you can process things incrementally. Okay, so if there's a print server, then it can just start printing incrementally, or if there's a display server, it can start displaying incrementally. But you might need to go and wait for, you might need to go and distinguish between the different parts of what you received. So in that case, you might have to go and scatter the gathered data so that you can separate that into the units in which the sent units. Okay. So can you guys imagine the opposite also? That the sending site scatters and the receiving site gathers if necessary. I mean, if you're doing byte communication, you might not have to do it. So we have gathering at the sending site. How about scattering at the sending site? Does that make sense? So yes, as you guys mentioned, if the message is really large, it doesn't fit into the network unit. UG, you want to raise your lower your hand? Um, then it might go and break it up into multiple units and send each unit individually. So sending system is scatter if necessary, and then these are the units that may be received. And so if you really need to process with the sent unit, then you might have to uh, scatter the messages. Yeah, and this can be quite tedious task. So you guys are going to do an assignment that involves byte level communication, but I'll give you a layer that does the automatic scattering and gathering. Okay, so we saw last time the various operations there are. We saw that there was, and we saw the various blocking times. So we saw there was this accept operation that was performed on a factory channel, and there was this connect operation that was performed on a regular channel. And when a message, the connect operation sends a message to the destination, and when it's accepted, the result of the accept is a new channel that is connected to this channel. Okay, so that's a new channel derived from the factory channel. That's why we call it as a factory channel that is connected to this channel, so that now we can send data between them. And what can you do? We model this as a character communication. So you can, a writer can put a character, and a reader can get a character. Okay, so these were the operations. These are the various times that we saw that can be used to determine when an operation invoker unblocks. Okay, and I defined synchronous and asynchronous operations very um, uh, in a very operation independent fashion. I said, look, there's a start time, there's the end time. They may or may not be the same, and if they're different, then there might be some communication of data. And if there's communication of data, then the data may be at this, may arrive at different buffers at different times. Okay. So now we have these four concrete operations. Um, if you know how sockets work, you should know what the blocking semantics of these operations are, and you probably don't remember. Um, so let's go and put on our thinking hats and say, look, if I was to go and design a channel semantics, and if I want to, as Randy put it last time, make sure that I favor the programmer, okay, which means I'm favoring blocking, so that so that or I'm favoring synchronous operations also. If you favor synchronous operations, then there's less overhead in programming. They're more like regular operations that are non-distributed. But if I really need to, if efficiency is really, really bad, and this is where you have to make a judgment call, then I'm willing to sacrifice programmability a little bit. And hopefully, I needn't sacrifice either. Okay. So we want to go and design the semantics of each of these operations, the blocking semantics of each of these operations. There are all these times, and we can pick from these times and determine what these operations, when these operations unblock. Okay. So let me go to your slide. So what would you make the blocking semantics of these operations, or what semantics do sockets support? That's sort of the same question, I believe, though you can maybe improve on sockets in some way. Okay, so we essentially derive the answer. So we block until, for connect, we block until server accepts connection to the factory channel. That is and that's the channel on which we do the accept. And the accept blocks till the next client tries to contact the factory channel. That means the next client sends a message. So accept will unblock before the connect will unblock. Okay, the message from here will go from here to the this end. It'll get accepted, and the connecting party will wait. And as soon as the message arrives, a new connection is established. And at that point, the server, the acceptor unblocks. And when the acknowledgement arrives here, um, the party that initiated the connection or the client unblocks. Okay. And we saw that we saw that we don't want to wait until the data reaches destination message to allow coalescing or later. And so this is the only asynchronous operation we have here. And but we do block. Okay, we will see later non-blocking versions of this. So here's what we could do. We've got the basic operation. Let's go and uh, keep our channel semantics, which are typically implemented with the kernel, um, as skinny as possible. And we can build libraries. So, and the library level, not in the channel layer, but in the library layer, we can have a write, channel write. And we can build it on top of the character write we had earlier, character put we had. And it can just go and invoke put multiple times till we've emptied the byte or the character array that we want to send to this channel. Okay, we can do that, or we can provide a write operation that's part of the channel. I guess I need to spell this right. So in fact, we do provide a multi-byte or an operation that allows an arbitrary number of bytes to be sent in the channel. We don't actually provide this. We don't assume that the application programmer will go and actually write such a library. Okay, even though such a library can be written. So there's a fundamental reason for doing so, which has to do with performance. And those of you who've done operating systems should be able to answer this question better. But I think you've heard enough from me in this class that either set of students should be able to answer, hopefully. But it is a subtle question. So why not do this in libraries? Why do this as part? So we would need to do a kernel call for each putc. So we switch to the kernel mode, and that's called a context switch. We're switching from user mode, user context to kernel context. And this is to distinguish it from process or thread switch, where you go from one thread to the other. So you don't necessarily go from one thread to the other, though often operating systems say, I've got you in the kernel. Let's go and switch you too. Okay. So there might actually be a thread switch also on each putc. Uh, because for you to switch to another thread, again you have to go into the kernel mode. So some systems say, okay, you're in the kernel mode, let me switch you too, so that we don't have to make another switch when your time quantum expires. Okay, so we don't want to do that, and so this is very important. That often, um, you know, whether something is synchronous or asynchronous or blocking or not blocking is often decided by the operating system, and also the operating system decides the size of the data transfer, and both are done for efficiency reasons. Okay, so if we allow byte array to be sent, then our connect and accept calls don't change. They don't really transfer any data. And now I'm getting closer to sockets. In fact, I've gotten very close to sockets. I'm using the exact same names, I believe. So we can have a write byte and a read byte. So then the question arises: what exactly does are the blocking semantics when I'm sending bytes rather than characters? Okay, so for characters, it was a little clearer. If that was confusing, this is going to be a little bit more confusing, and that's part of the reason why sockets become hard to understand. So I think I have this question. So what are the blocking semantics right now for write and read? Okay, then. So we are going to, as it turns out, we block until at least one byte is in system buffer. So we don't block until the whole everything can be sent. And again, as I said, that we want to think of file transfer as an application. So why delay processing? If you're sending a really large number of bytes, why not allow some bytes to be sent before others, so that the other end can start processing them before, um, uh, uh, and not wait for the entire data to be written. Okay. And again, what is chosen by is block until at least one byte is received. And like David said, this allows us to start processing things incrementally. And these two operations go together, right? Here you don't block until the whole array gets sent, and here you don't block until the whole array has been received, so that you can have pipelining of operations. And also there's another part here for read that we don't quite know um, how many bytes may be received at the other end. So we might just give a very big byte array and say, okay, here's the largest space I have, and fill as much of it as you can, and unblock me as long as you can fill some of it. Now, David said, look, this has got the danger that you might have to make more system calls. Indeed, you will make more system calls this way because you have, and not only that, your programming becomes much more tedious because you have to write, and then you get an indication of how much was really written, and then you have to write again with the remaining part, and again get an indication of how much was written till everything was written. So when sockets came around, there were textbooks on how to go and write this loop. And similarly here, you want to receive data, and if you really need to go and collect data, you're not doing incremental processing, then you have to make multiple calls till the expected number of bytes arrive. Okay? So your programming becomes more tedious, and indeed you make more system calls. But typically what's going to happen is that you will have a lot of space. That a partial write will occur only if you've got an unexpectedly large amount of data. And it's okay to go and make multiple kernel calls as long as each kernel call involves a large amount of data being transferred. We're not doing it per byte, remember? We're doing it each time we don't quite finish writing the remaining bytes. Okay? And typically, a packet will arrive here with more than one byte of data. So typically, you are not going to unblock with one byte. You're going to unblock with a whole packet full of data. So again, your read calls will be amortized by the number of by the size of the buffer that gets filled each time. So it's not really that much of a cost. Okay. So that's what the other semantics, and it is somewhat confusing, but if you think about it, it's a good balance between performance and programmability. Okay, and you're not quite polling, okay, because each time you will block. So you would poll if you unblock if there's even 0 byte in system buffer, okay, or 0 byte received, and we will see those semantics also so hopefully today. So this increases concurrency. This allows this pipelining mechanism that I talked about. Okay, so that's good. We can send byte arrays, and that's a good data structure. But as it turns out, byte array is not. Um, that's the initial data structure people have used, and it was succeeded by another data structure that allows reuse of buffers more easily. And I said that, look, we need to know how much was written or how much was read, and that is typically returned as a return value. And you want return values of various things, such as status. So why not have a data structure that has in it, built in? So how does the application know how much was written and read? Return values. How to reuse read or even write buffer? Well, we will go and have byte array with pointers that will not require return values. Okay. So Java byte buffer with pointers, we need some storage. Okay, and typically what you do is out of a byte array you can create a byte buffer. Okay, that's what I've done. So we go and allocate an array of bytes. Okay, and you wrap that up in a data structure that has some pointers. It doesn't have one pointer; it has multiple pointers, and I'm going to show you only 3 of the 4 pointers I know about. So the size of available contents, okay, that's the capacity. Okay? And it's pointing one element after the last index. Position of next element to be read or written. Okay, so that's position. So you're either writing to the byte buffer or reading from the byte buffer. So that's the position. When you're reading, then you need to know what the limit is. how far you should read, because the byte buffer may not have been filled to capacity. Okay, so there's a pointer called limit, and you always have this in where this relationship: position is less than or equal to limit is less than or equal to capacity. Okay, so that's a data structure that is used with which you will be using, in fact, in your assignment number 6. So let's go and see it being used. So let's say we want to produce data into a buffer. Okay, so we want to go and write a byte buffer. So before writing the byte buffer, we need to fill it up. Okay, so how do we exactly fill this byte buffer up before we send it to some channel to write? And we can even write to a file. Okay, so out to some object that allows write of a byte buffer. Okay, you'll first go and clear the byte buffer and make the limit be its capacity. So we're writing, so limit will be capacity. We can write to capacity. So we clear at this point where position becomes 0 and limits becomes capacity. Then you can go and put data, and let's say we are sending a string, so we can convert string into bytes in the manner I've shown you here. And then our position has changed, our limit on capacity have not. And we can now reuse the same buffer for another message too. Okay, so we can do some internal buffering ourselves before we send it out to the channel or the file. And now what we do is we say, okay, we are done. So we want it to be read. So we do this flip operation. What did flip do? It made limit be the original position, because that's the point till which we had written, and made position become 0, so that now we can read from here till this point. Okay. So let's see what happens when we're reading it. We go and read a certain amount of data. So here I've first read some bytes and converted the bytes to a string. And so I read till my position reached the limit, essentially. So we consume the data. And once we're all done with this, we can clear it and go to the original situation. Okay? So this is a typical example of how byte buffers are used for both reading and writing. Okay, this is the API, Java API will tell you this information, but people make a lot of mistakes, so I figured it's good to have a graphical description of what's going on. But otherwise, there's nothing fundamental about this data structure. And it's important that what you send in a byte buffer, even though you're sending a byte buffer with pointers, etc., I should have a parenthesis here. What you send is not essentially what will be read, okay? Because the message may be scattered or byte buffer or gathered. So this is very important. Okay, I've been inspired by sockets, but I've been working at an abstract level. I've talked the term channel or port. I've talked of server channel factory. These are the terms that made more sense to me than the terms used in sockets. And then I've talked of put C and get C to make sure that we are reading, to indicate very clearly that we're reading and writing characters. Okay, so that's conceptually you've got everything from here. But if you start coding, you need to know the exact API of the system you're going to use. And to make it concrete, it's good to map this to a real. So here's what happens in the Java world. I told you there are two kinds of channels. There's the channel that is a factory channel, which produces the regular channel. So there's regular channel and factory channel. So these are called server socket channel and socket channels. Okay. So now servers on the left, and this is our factory channel, and this is a regular channel. Okay. From channels, we can get sockets. Okay, so the channels have pointers to sockets. Okay. Sockets have a regular input stream and output stream semantics. So they are derived from the regular I/O. Okay, terminal I/O and file I/O. No byte buffers here. Okay, you want byte buffers, you use the socket channel and the server socket channel. Okay, and how do you create these channels? You want a regular socket channel, you go and invoke a factory method called open to create the socket channel. You want server socket channel, you invoke a factory method called open on server socket channel. And again, in my terminology, this channel itself is a factory channel, is itself a factory that creates channels like the socket channels at the server end also. Okay. And you do accept on this factory channel, and you can do accept on the socket also. Okay, so this both uh, both of these have this operation, and you do connects on the socket channel, the client end, and you can do connect on the socket also. Okay, so we've seen IPC. We saw that last time, and now we've seen blocking IPC and what it might mean. So the next step is to go to non-blocking IPC.